This is complex regression. Okay. We actually started multiple linear regression the other time. And of course, we've considered combination of both categorical and quantitative predictor in a model. And we want to continue from where we stop, considering an extended form of a multiple linear regression model. So in the outline, I'm going to walk you through polynomial regression again, then multiple linear regression with non-linear effects. And finally, talk about polynomial with several predictors. So let's get started. Let's start with the polynomial regression. Okay, now when you take a look at the first one here is actually called, this is a second order polynomial in one variable. When I say one variable, this is having one predictor, one explanatory variable, except that we're looking at it in both linear and quadratic time. Okay, and take a look at this. This is having a second order polynomial in two variables. What are the two variables? X1 and X2. If you take a look at here, we consider X1 and X2 in a linear form. We consider it in a quadratic form. Then we also consider their interaction. Take a look at that. Okay, I just wanted to see that. We got different kinds of polynomial regression model from one variable to two variable and so on like that. Now, I want to focus on a polynomial regression in one variable that we call a quadratic regression model. Now, I want to talk about this guy here and this guy here. Okay, now we take a look at beta 1 is a slope for x, and that x, the way it appears in the model, it appears in a linear form, and therefore the beta 1 associated with that we call a linear effect parameter. Does that make sense? That's a linear effect parameter. Okay, why beta 2 is actually going to be a quadratic effect parameter. Why is it a quadratic effect parameter? That is acting like a slope for x squared. Does that make sense now? Okay, and if I want to generalize, if I want to talk about kth order polynomial, okay, this is a kth order polynomial. Don't forget, this is still one variable, just one predictor. Only that we're having the linear effect, quadratic effect, and so on like that. Okay, is there any question here? So this is a kth order polynomial model in one variable. But you know what? I want to walk you through now. When we have from polynomial of degree 1 to degree 2 to degree 3 and so on like that, how many bends are involved? But we got a formula, okay? We got a formula. Take a look at this guy. I said there is one less bend than the highest order in the polynomial. If I want to know the numbers of bend, okay, that we're going to have, okay, now the numbers of bend will be equal to the highest order minus 1. Now I'm gonna start with this now. You're gonna see what I'm talking about. Take a look at this guy. That's a linear, right? That's a polynomial of degree 1, right? Polynomial of degree 1, how many bend? That'll be 1 minus 1, 0 bend. There's no bend. Is there any bend in a straight line? Take a look at that. Is there any bend? No bend. Okay, now when you come to the polynomial of degree 2, the highest order is 2, then the numbers of bend is going to be 1. That will be 2 minus 1. So in the case of a quadratic one, how many bend? That will be 2. Do you see that? That's a bend. Someone, another one. Is there any question? So the general idea here is just to tell the world that, okay, you know what? If I really want to know the numbers of bend that we actually going to have, okay, that depends on the power, the highest degree of the polynomial. So it's just going to be the higher degree of the polynomial minus 1. Okay, now let's look at the application of this guy. But there's something I actually want to mention. I said the highest order regressors determine the overall shape of the relationship. Okay, now what am I trying to say? Okay, what is the highest order here? The highest order regressor, you know, is one. X is raised to power one. What is the slope? The slope is B. Okay, that determines the shape. That's what we mean. Now, when I come here, what determines the shape in the quadratic? It is going to be that very C, because that C, that parameter corresponds to the highest order. Does that make sense? That's what I mean. And I said the highest order regressors. Okay, the highest order regressors determine the overall shape. So which means this guy here is determining the overall shape, and C is a contribution if I want to know the value of that particular shape that I'm talking about. But another thing I need to pay attention to, what about sign? Okay, the sign on C may be plus, may be negative. Now, and I said the sign of the coefficient for the highest order regressor determine the direction of the curvature. Please pay attention. Okay, I said the sign of the coefficient for the highest order regressor determines the direction of the curvature. What is the highest order here? Okay, S is to the power 3, right? Okay, what is the coefficient for that? D. What does D? The D actually will tell us the shape, and the sign tell us the direction of that. Okay, the direction of the curvature. Does that make sense now? Okay. Now I'm going to go into an example right now. How does the numbers of electives taken in an area predict interest in further electives? Maybe some of you are not in statistics and you've taken an elective courses in statistics before, and I want to believe maybe what you increase your interest in taking further elective in statistics may depend on something, maybe your experience, the first time. Now, we want to answer a research question here. How does the numbers of electives taken in an area predict interest in further electives? Now, if I want to do that, I generate a scatter plot between interest and electives. And I'm seeing something that look like that doesn't look like a straight line. Okay, I look at the plot. I'm seeing the violations, okay, of normality. Okay, and I look at some, I look at some other thing as well. I'm seeing the violations, and that is telling me I actually need, I don't need a model with no bend. Okay, I need a model with at least one bend. Okay, and if I want to try that, the very first model I'm actually going to consider is to start with a quadratic a quadratic regression where I have one bend first. Take a look at this. When I run the model for linear, that is the output. What is the R squared? When I look at, here, I'm looking at the relationship between interest and electives. I actually conducted a linear, I use a linear model. The R square is 0.5608. And when I incorporate it, take a look at this now, the quadratic term, okay, of elective squared. You see that now? The R square goes to 0.6726, indicating an improvement, right? Take a look at that. And if I really want to know whether the quadratic term introduced is significant, I have to look at the p-value, right? I have to look at the p-value. The p-value here is less than 0.05. That indicates significant. That should be included. We need a quadratic term in the model. If I don't want to write let's say, actually want to write the fitted model out for both. I want to write the fitted model out for both. Okay, these are the fitted model for linear one. Can you see the linear one? And can you see the quadratic one? I can plot, I can plot the two. If you take a look at this, to be able to tell the world, the one that matches the reality. Okay, the relationship is actually quadratic one. Okay, take a look at that. Now, this is the situation. This is a question now. When I incorporate quadratic effect into the model, that led us to an improvement. Now the question now is, should we actually consider higher order polynomial? We may want to ask that question because considering no bend, we saw what happened. Considering one bend, we saw happen, and we saw an improvement. Can we just think of, considering higher degree of polynomial like that? And that's why I said, how can you test if more complex model, that is a cubic, is needed? Okay, the only way to test is to test statistically, incorporate that, and check for the p-value. Now, do you see this guy now? What do you see? Raised to power 3, right? Okay, and if I really, I wanted to pay attention to something. What happened to r squared goes up, but let's say initially um is 0.67. The r squared didn't go up much, right? Even though r squared increases, but that's a marginal increase. But r squared shouldn't be a yardstick to measure or model or performance only. You know what I'm going to do if I really want to know whether the cubic effect that I've introduced as effect, what I'm going to do, I'm going to look at the p-value. What has happened? We don't need it. Even though r squared goes up, even I can see from the way r squared goes up because of marginally. That's not significant increase, So take a look at that. So if I want to ask a question on whether I should consider a higher degree of polynomial, of course, we're actually going to look at the p-value associated with that effect introduced. Okay, and let me also tell you this: in statistical analysis, uh, we should have a reason beyond data to include any polynomial that will be higher than degree, that will be higher than cubic. Because the more you actually go for higher degree of polynomial, even though the r square is going to go up, but it may not make sense. Okay, so but we can still tolerate up to third degree of polynomial. That's no problem. But whatever degree of polynomial you're incorporating, we have a way to conduct a test to see whether we should justify its inclusion. Is there any question before I go to multiple regression with nonlinear effect? Is there any question this time? Whether in person or online, you're good, right? Okay. Now I want to go into multiple regression with a nonlinear effect. And we got a research question that said, describe how to test a nonlinear polynomial additive effect of mice on 5K times, controlling for age. Okay, now what do I want to do? I actually want to compare two models. One is a compact model with only age as an explanatory variable. And I got an augmented model where I add mice and the square of mice. The square of mice is just going to be a quadratic incorporating a quadratic effect. And what did I say in 3? I said test the coefficient of whatever you introduce. Okay, indicate if the effect of training mice on races time changes based on numbers of mice. Okay, S squared depend on S, right? Mice squared depend on mice. Does that make sense? Okay, so then if you take a look at number 4, the coefficients for C mice, okay, indicate the effect of mice for someone who scales on average, okay, average numbers of mice. We can do model comparison, and at the end of the day to be able to see which one work. Now I'm going to show you something now. Oh my God, you know what I'm doing here? I'm only doing a simple linear regression where people run mice with consider time. of our Olympic trial is actually on the way, and you want to you want to see the role of age in the numbers of time you turn in when you run a race. Okay. Now, when you're looking at the effect of age only, can somebody cite the R square for that one? This is that's a poor model, right? Okay. Now, what do we do? Do you know what we did? We introduced mice and we introduced the square of mice. Okay. But whatever we introduce, we got a way to investigate is how significant they are. Now, they take a look at this guy. Oh my God. Look at the p-value. And that's of the square of that. Can you see the p-value? It means whatever we introduce, we got a statistical justification for that because the p-value is less than 0.05. And not only that, oh my God, not only that, look at the R squared, from 22.45% to 72.71%, that's a lot of increase. Is there any question here? We don't just do what we do. There's a reason why we do what we do, okay? In statistics, we actually have a reason to justify whatever statistical action we make. Any question at this time for moving forward? Okay, now I want to go into second order polynomial in two variables. I've been talking about first order in one, second order in one variable. I want to talk about in two variable. Take a look at this, x1, x2. I got two explanatory variables. Now I have them specified in a linear form, and I also have them specified in a quadratic form. And not only that, we also incorporate interaction. Okay. And that was why whatever variable you introduce, I'm trying to tell you now, your beta one, beta two, actually they are linear effect parameters. And beta one, beta two are quadratic effect parameters. And beta one, two is interaction effect parameter. Now let me tell you this. When do we consider interaction in a regression model? Okay, we consider interaction in a regression model because two variables could have a combined effect on a response. Okay, now, and another reason why we consider interaction is to talk about conditional relationship. For instance, the way x1 relates to y may depend on x2. The way x1 as an explanatory variable, okay, relate to y, a response variable, may depend on x2. In a situation where an explanatory variable depends on another explanatory variable, then we need to consider interaction effects. But let me tell you this, we got a way to actually test the parameter associated with the interaction effect in a regression model. All what we just need to do is to look at the p-value associated with that. Now I'm going to go into an example now. Oh my God, you know what I'm doing here? I want to talk about baking, okay? And if x1 represents temperature, in baking, right? You need temperature and you also need a time, baking time, right? And if y represent average palatability score, okay? Now, what I'm looking for here, I'm actually looking for the optimal temperature I'm going to set. I'm also looking for the optimal time because it is not just a matter of, oh, let me just increase temperature all the way, increase time all the way. What will happen to what you are baking is going to get burnt. So we need optimality here. We need optimality. We need to be able to figure out what is the optimal values of x1, what is the optimal value of x2 that do I need before I could actually get what I need. So in that situation, we actually need not only quadratic effect of each variable, we also need the interaction effect because the way temperature will relate to the response variable here may depend on time. Okay, now in the end, oh my God, in the end, take a look at this guy now. All of them are significant. Look at that. Interaction effect is significant. Okay, the quadratic effect of each variable is significant. The linear effect is also significant. Even when you take a look at the R square here, oh my God, the R square is so high. Look at that. Okay, now how do I write my fitted model? How? So if I want to write, um, okay, another thing I'm going to say, uh, there are so many ways we can write a code when it comes to multiple linear regression with nonlinear effect. Look at POLYM, poly. That's a poly, X1, X2. Then I only need to specify degree equal to 2. Okay. If I'm going by this, it's automatically going to consider both quadratic effect and interaction effect. But let me tell you, there are so many ways to do that. Of course, my TA will walk you through all of that in the lab. But you know what I want to do right now? Okay, so how do I actually write my fitted model? Of course, I'm going to need a combination of that. If I want to write, oh my God, can you see my fitted model right now? Look at it. That's where my fitted model is going to be. Okay, intercept, you can see the linear effect, the quadratic effect, as well as the interaction effect. Is there any question on this? Any question? Go ahead. Yeah, but we're still going to like right now we haven't found. I'm going to say this. That's a good question. These are not the optimal values for now. They are just the estimate of the regression. These are the estimate of regression parameter. But you know what we're seeking for? We're seeking for the optimal value of x1 and x2. These are just the optimal value for the parameters, but not for temperature, not for time, baking time. Okay, but I'm going to walk you through that. But before you can get an optimal value for temperature and baking time, you need to first get this. Okay, now after getting that, okay, I'm going to show you something now. Okay, take a look at this. Okay, sorry. Before, let me also, this is another way to write a code. This is the one you are used to. Just write y on x1 plus x2. Then don't forget, you have to put indicator. You remember that we did that the other time? I on that. Okay, I on that. Then plus the product. That product indicate interaction. And the name of my data is cake. And that actually give us this. Okay. Now, the next thing now is look at the question we want to answer. Estimate the optimal x1, x2 combination, okay, and the standard error for that. That's what we want to do now. Okay, you know what we've gotten before. We've only obtained the linear the regression, the estimate of regression parameters. Okay, but what we want to do now, we want to obtain the optimum value of x1 and x2. Then we're actually going to apply mathematics approach, optimization. Please, I need you to pay attention now. We are in a critical period now. Okay, this is the model, right? Okay, which is this guy here, which is um which is this one, right? If I want to get the optimal, or if I want to use optimization technique, then I'm going to differentiate. I will differentiate what I have here. Don't forget, this is coming from regression output. I'm going to differentiate this with respect to x1 set to 0. I will differentiate with respect to x2 set to 0. That's what I'm doing here. I'm going to show you now. Do you see that? With respect to x1 and with respect to x2. And after that, we're going to equate that to 0. Then we solve for x1 and x2. Now, what I'm trying to tell you now, I've already done that. You don't need to worry yourself about it. This is it. Now, what are we talking about? The optimal values of x1. You can see I put something on that. Meaning, oh, it is not just baking time, but an optimal baking time. Oh, it is not just temperature, but optimal temperature. What do you see here? This is a function of the parameters in the table. You see that B2, B5, we got B2, B5 in the table. Okay, we got B2, the B2, B5. Look at that. This is B2. This is B1, B0, B1, B2, B3, B4, and the B5. And all of that, they are here. They are here. Do you see that? The B0 is negative 220. The B1, the B2, the B3, the B4, the B5. Okay. Now all you just need to do is to plug in those values. Okay. Do you know when you plug in those values, you'll be able to get the values of X1 and X2? You can see it's a two-stage process now. Before of us get your regression output in place, you write a module, feed a module, then you perform a calculus, differentiating that with respect to X1, we set to 0, we solve for X1, we differentiate with respect to S2, we set to 0, we solve for S2, and that come out to be this. Okay, now if that come out to be that, don't forget, okay, all what we're going to use, they are here, right? That's a beta naught up to beta 5. You can see that. Okay. So what I'm going to do right now is actually to write, using the formula now. Do you see what I'm doing? But let me tell you this. We can actually you can code the formula. Okay. And write this. Do you know what I'm doing here? I'm coding this guy. B2 times B5 to be able to use an R, okay, which is what I have. You see that? Do you see B2 star? Do you see B2 star B5? I'm coding that. And after doing that, I'm going to write data method M1 dot M that the moment I do that, I'm actually going to have a result. Now, you know what it's giving me? This is the optimal estimate for X1. This is the optimal estimate for X2 and with their corresponding standard error. So the moment you actually write the code, it's automatically going to generate. But before writing this code, you need to code your expression for X1 and X2. Does that make sense? Is there any question here? Is there any question? You saw? Oh, you want to say linear module? No, this one here, let me just say, oh, you mean LM is linear model, right? M1. Okay, let me tell you what M1 represent. Is the model that you've run before, which is a linear model. Yeah, M1. Yeah, you're right. Which is a linear model. And you know M2 dot mass, right? The M2 dot mass, of course, you can see, you see the code in here. This is very, very crucial. Can you see these two here, right? These are very, very crucial, right? And how do we code this? How do you know what to code? We code the mathematics here. This is what we code. Okay. And the moment you do all of that, you're just gonna have. So what is telling us now is that your optimal baking time and the baking time and the temperature. Okay, maybe this one is the optimal temperature and this is the optimal baking time. Okay, that's what we have with the standard error. Okay, now the next thing I want to talk about is I want to look at want to take a look at this hemoglobin versus oxygen. Everybody know that oxygen is very, very crucial for hemoglobin. Okay, now when I do a scatter plot of that, you can see what we have. It's looking like a curve in a way. Okay, now and if I want to fit a model, at least I should fit a polynomial model. Okay, take a look at this of a degree 2. Okay, you can see here I have oxygen and oxygen squared, right? Okay, and you see how square is very, very high. But I want to show the world that if I actually what if I decided to do this? Take a look at this. This is the analysis. okay, that come out of that. But let me tell you this, whenever we use polynomial, we have violated an assumption. I'm going to say that again. Whenever we use polynomial, we have violated an assumption. And what assumptions have we violated? Take a look at this. You know, this is oxygen, right? And this is oxygen squared. Okay. We have violated assumptions of multicollinearity. You know, in a linear regression, variables, explanatory variables should not correlate. Okay, that is what we call, let me write it, multi is one of the assumption that's, so let me write multicollinearity. Okay, multicollinearity is a problem in a multiple linear regression. You know, we require that explanatory variables should not correlate. But let me tell you, oxygen and oxygen square will correlate because oxygen square depend on oxygen. The values of S square depend on S. Okay, and how am I going to know whether multicollinearity exists in a multiple linear regression model? Okay, we have an arrow code for that. We call it VIF. We're going to run a VIF, and we have a threshold for the VIF. Okay, you know, when you do M1 the other time, you know, when you run the model, like if I want to know, when you run, you know, the model is M1, right? You know, the model is M1. If I really want to know whether multicollinearity exists, I'm just going to write VIF into M1. Please write it down. My TA is also going to walk you through that. VIF means variance inflating factor. Variance inflating factor. So that will automatically give you the VIF for all the regression parameters. And let me tell you this. What is the threshold? When VIF is greater than 5, then it is problematic. Now, take a look at this. For oxygen and for oxygen squared, what is the VIF for them? 99. You see the VIF for them? It's 99.94. You see the VIF? And what is the threshold? The VIF should be, the threshold is, it shouldn't, if the moment is greater than 5, okay, when the VIF of your coefficient is greater than 5, then there exists a multicollinearity problem, and it means that particular variable is actually going to be problematic. Does that make sense? Okay, now how can we, so every polynomial regression actually have this problem, but what can we do, you know, to correct that? Okay, I need you to pay attention right now. Okay, but what we can do to correct that is we can do centered. We can do what we call centered. You know, there's something we call centering, but but before going there, let's first get the descriptive statistics first for the variable. Okay, I got 30 observations. And what does it mean? It's 50.64. Okay, the minimum and so on like that. And you know, when we run the regression, this is what we have. Okay, even though oxygen is significant, oxygen square is significant, but there's a problem with the VIF. You see the problem with VIF? What is the threshold? The threshold is 5. When the VIF is greater than 5, that will be problematic, and that's not good at all. Okay, then what are we going to, and this is a way to show that correlation exists between a perfect correlation, very close to perfect exists between oxygen square and oxygen. You can see that straight line. Now, what can we do to correct this situation? But before we know what to do to correct the situation, now, please, I need you to pay attention. What we're going to do is I got Y and I got X and S squared, because S squared depends on S. Okay, there's a violation of assumption. One of the assumptions of multiple linear regression is, you know, no multicollinearity. Multicollinearity is when uh, variables in the model correlate. Even though we want response to correlate with them, but we don't want x and x squared to correlate with themselves. But with what we're seeing, they're going to correlate. But how do we correlate it? You know how we're going to correlate it? We're going to recompute. We're going to have a new s that we're going to call s star. And that s is going to be what? X minus the mean of x. Can you see that? That's what we call centering. S star is going to be x minus x bar. Okay. Now we also go to, and the moment you get that, then you now get x star squared. You square that. Does that make sense? Now, when you centered, you have removed multicollinearity effects. Does that make sense? So centering is removing the mean from the respective observation. And at the end of the day, you are now going to use y against s star and s star squared. Does that make sense? And when you do that, please, I need you to pay attention now. Okay, I need you to pay attention now. I need you to pay attention now. Okay, when you do that, when you want to interpret your beta naught, you remember the way we normally interpret beta naught. We're going to say the values of y when s is 0. We're not going to say that here after centering. You know what we're going to say? We're going to say the estimated coefficient beta naught is the predicted response y when the predictor s equal the sample mean of the predictor, when x equal to x bar. Does that make sense? When oxygen equal to the mean of the oxygen. That is the way we're going to interpret beta naught. How do we interpret the beta one? Of course, the beta one will be interpreted the same way, similar to simple linear regression. But how do we interpret the beta 2? Don't forget, the beta 2, I told you the other time, the beta 2 correspond to the highest degree, right? Which will indicate the direction. And here it's going to be, when it is less than 0, it's going to be, the curve is concave down. When it is greater than 0, it's concave up. Does that make sense? Now, I'm going to show you something really quick. Now, please pay attention. After centering, how do we know we have removed multicollinearity? After centering and we rerun the model, look at the VIF. The VIF is less than 5. No problem anymore. Does that make sense? So which means I'm still going to do, after, maybe you can call the new model. You know, we'll be calling that one M1, right? Call this one M2. Now M2 now is where you regress Y on S star and S star squared. What is your S star? X minus X bar. Does that make sense? Now, and you know what we're going to pay attention now? Look at the estimate here. Will be totally different from uncentered. I'm going to show you the one you get for uncentered now. Can you see the uncentered one? Are they the same? They are not going to be the same. Okay, why is it that we cannot trust this, even though the p-value is fantastic? Because there's a problem. Do you know they can make a good judgment in a court, and that very court does not have a territorial jurisdiction? If somebody commit an offense in Minnesota and the person ran to California and the California court tried the person, even though the California court was able to establish the fact that they commit the offense, they are doing the right thing, but they are, they don't have a territorial jurisdiction. Does that make sense? Even though the p-value, looking good, right? But there's a problem. Okay. And now am I going to know? I'm going to do VIF again. The VIF of M2 of the new model, okay, the VIF of the new model, oh my God, the VIF is now 1.05, then which means after centering, okay, the VIF is less than 5. We've already removed that multicollinearity effect in a statistical model, statistical analysis. When multicollinearity exists, one of a way to resolve multicollinearity is through centering. Okay, let me write it. Centering. Can you see that? And what we mean by centering is just, you get a new x, we call it x star, which is going to be x minus the mean of x. Does that make sense? That's what we mean. Okay, now, how do we now interpret. For instance, we want to interpret what we got. You know what we want to interpret? We want to interpret this guy. But let me tell you this. After centering, the way we interpret is different. The way we interpret intercept is different. The way we interpret intercept before is what? We're going to say the values of y when x equal to 0. We're not going to say that here because we have centered. Okay, don't forget we do x minus x bar. Okay, we're not going to say we're not going to say x equal to 0 again because we do x minus x bar. We're going to say x minus x bar equal to 0 because this guy is what? S star. So S star equal to 0 means x minus S bar equal to 0. If x minus S bar equal to 0, what does that mean? S equal to S bar. Does that make sense? S equal to S bar. Now, look at the way I'm going to interpret 163.2.3. Look at the way it's going to be interpreted now. You're going to see now. What did I say? I said the estimated coefficient B0 1632.3 tell us that a male whose maximal oxygen uptake is 50.64, okay, 50.64, that 50.64 is the mean of the oxygen. 50.64 is predicted to have 1632.3 mg of immunoglobulin in his blood. Where is this guy coming from? That is the mean of the oxygen. And what do we say here? Take a look at what we say here in the IROS. There's something here. Please pay attention. I said the estimated coefficient B0 is the predicted response Y when the predictor S equal the sample mean of the predicted value. Don't forget your S star equal X minus X bar. And if that equal to 0, then it means S equal to S bar. Okay. Now, how do I interpret the second one, the 34.0 for the oxygen, and the other one you're going to see right now? Okay, now take a look at this. I said estimated coefficient B1 34.00 tell us that when an individual maximal oxygen uptake is near 50.64, near the mean, that is the mean oxygen, near 50.64, we can expect the individual hemoglobin to increase by that. Okay, increase by that because that's a positive, right? If it is a negative, we're going to say decrease by that for every one increase in marginal oxygen uptake. Look at that. That's the way that is interpreted. Okay, and do we need interpretation for B2? The B2 is only going to tell us the direction of the curve, whether it's going to be a concave up or concave down. Okay, take a look at that here. I mentioned that here. You say B2? Okay, but it's just going to give us a mathematical explanation. Like, okay, when B2 is less than 0, it's going to be concave down. When it is greater than 0, it's going to be concave up. And you know, here it is positive. Oh, sorry, let me see. Yeah, it is negative. You see negative? Okay, that means B2 is going to be less than 0. Okay, and less than 0, based on what I put here, that's going to be concave down. Okay, so take a look at that. Less than 0, that's going to be concave down. So the real, so you can now see, and the 50.64 I'm talking about is the mean of the oxygen. Don't forget, we've gotten that from day 1, which is the mean. It has to do with the oxygen, because when in a regression modeling, okay, most of the time, whenever there's a problem of absorption violation, maybe we need to transform the variable X. We've been transforming the variable X. But let me tell you this. Our intervention could also create a problem. We want to solve a problem, right? At times I normally at times I think a lot, like somebody commit an offense, maybe, and the person get killed, or I'm like, is that the right thing to do? I don't know, So we are trying to solve, at times we're trying to solve a problem, but the question is, are we also not creating another problem? Like here now, just like what somebody said in this class the other time, multiple, applying polynomial regression is an intervention because we believe that the conventional linear regression cannot, cover the curvature, depict the curvature in the relationship, and we're bringing in the quadratic effect, okay, with the belief that, of course, bringing a quadratic effect, we actually capture the relationship, but it's also going to create a problem, right? Okay, because in the multiple linear regression, if I incorporate s squared and where I have s squared depend on s. This happens to all polynomial regression. Okay, now what are we going to do? We shouldn't be celebrating looking at the p-value only. No, we shouldn't be celebrating looking at the p-value only. Okay, we're also going to we're also going to talk about, like, okay, is there any assumption that is violated? And we'll know. And how am I going to know if assumption is violated? Or multiple, because all the assumptions of that we've done in simple linear regression, they are also for multiple linear, but multiple linear regression has another additional assumption, which is multicollinearity. That's okay, two variables in a model, particularly if they are regressor, they shouldn't correlate. When they correlate, even if the p-value is actually it's a good sign, that cannot be trusted. And at the end of the day, so what you need to do is to center, and after centering, look at the VIF again to see whether you've corrected that, and be careful the way you're going to interpret. The interpretation is no longer going to stay the same. You're going to be centering on average. Okay, this is where, okay, we're able to finish. That is the end of the material. Is there any question today? Is there any question? Go ahead. I said that again. Oh, how are you are asking, how are you going to write a centered fitted model? Is that what you mean? Now, it's easy. You know what you're going to do? Here is the same. Instead of you to write X, just say S star. If I want to write this now, you know what I'm going to do? That's a very good question. What I'm going to do is I'm going to write Y cap, right, equal. For those of you online, somebody in class asked a beautiful question that how are we going to write a fitted model for centered? Okay, so you're going to write 1,632.3 plus 34. Okay, because of my time, let me just write 34. Then I'm going to write X, but I'm going to put star. Can you see that? Then minus 0.536. Then I'm going to put S star squared. But here I'm going to specify, I'm going to tell the word what my S star represent. My S star represent X minus X bar. Have I answered your question now? Okay, and that is the reason when you want to interpret the intercept, we normally set this. It's not S that you set to 0. You set S star to 0. And the moment you set S star to 0, you know what that means? It means X minus S bar equal to 0, which means S equal to S bar. And that was why in the interpretation of this guy, in the interpretation of that guy, we were focusing on that, the mean. Okay, we believe the predator, the oxygen equal to is nearly the mean oxygen. And that was why take a look at the interpretation here. Can you see that? I said, because this actually centered on male, I said the estimated B0, that guy tell us that a male whose maximum oxygen uptake is 50.64, that 50.64 is the mean oxygen. Mean, okay? Then it's predicted to have that mg of hemoglobin in his blood. Does that make sense? That's super cool, right? That's a beautiful question. Okay. In the absence of question, make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you.
You're welcome.